Zakine here, assistant professor of the hydrodynamics lab in Ecole Polytechnique, and he will talk about his work on socioeconomic agents as active matter in non-equilibrium Sakoda-Schelling models. So please take it away.
Thank you very much, Wout, for the introduction, and thank you for inviting me. So I come indeed from the field of statistical physics, active matter, and non-equilibrium systems. And this is how naturally I was interested to socioeconomic agents and to understand the phase transitions in the socioeconomic systems. So this work is a joint collaboration with Michael Zakine, who was my postdoc advisor, and Jérôme Garnier-Brun. So a first work on these, where we build the model on these socioeconomic agents, and the second work where we try to leverage the tools we have developed in the previous model to enrich the model with the two populations that interact. And I will present these two papers and the results associated to that. And so where are we? Okay, what is the field we're talking about? Okay, we're talking about statistical physics here. So I start with a very broad introduction. We would like to describe the systems with a lot of particles. So when you have a few water molecules, you'll find with Newton's second law, but we have an Avogadro number. It doesn't work anymore, so you have to resort to statistical mechanics to better understand the collective behavior and predict the emergent behavior of the system. So this is what you do if you want to understand the phase transitions between vapor, liquid, and ice here for the water. And what is the general approach? So in equilibrium, and this is what I'm going to talk here, or to present here, usually, and we owe this approach to Boltzmann and Maxwell, you cause grain, you reduce the number of degrees of freedom, you find your relevant observables, which is the pressure, the temperature, the density, okay, anything that seems relevant, and you look for discontinuities in your system, the broken symmetries, and this is what you call phase transitions. And this works tremendously well for many systems, to understand the transition between solid, liquid, gas, okay, ferro-paramagnetic, superfluidity, isotropic, nematic liquid crystals that we need to the gene, okay? But this only works, this simplistic approach only works only if the system is equilibrium, in the sense that you can forget about the dynamics and just look at the coarse graining of the degrees of freedom to hope having a big function, being observables that you study. So this, when I say equilibrium, it means that we have a time reversal symmetry and no entropy production. And it turns out that in the last, I would say, 20, 30 years, we have an increasing interest for statistical physics of living systems, okay, and complex systems as well. And these systems, most of the time, are out of equilibrium in the sense that they continuously create entropy. And because of that, there is no such thing as a conserved free energy that you can minimize. So the system I'm talking about are typically active matter systems. So we have particles that locally inject energy or momentum in the system. More like these are very recent examples, very funny one of dense crowd, bacterial colonies, okay? More old ones that are neural networks and spin glasses, and the one we're interested in today are socioeconomic systems. Of course, you can ask questions. So this is a very broad introduction, but don't hesitate to ask questions. Okay, so in these systems, it's challenging to find one quantity that everyone would like to minimize. So every agent has their own utility. A common goal to optimize, maybe, I mean, if the state is involved, but the moralistic approach would be to say that agents try to improve their own satisfaction, probably at the expense of the wider population. And the system is a priori irreversible because there is no reason, I mean, my decision will affect a person in a different way that the different person will affect me. So there is no reciprocal interactions. there is no time reversal symmetry, and so the dynamics is important. So we are going to build a microscopic model relying on the dynamics. And this subject has interested a lot of people. So it dates back to actually to Sakoda in the 50s and then Schelling in the 70s, who tried to propose and advocate actually for simulations simulations of discrete people on a lattice to understand phase separation among human groups. So this resembles a phase transition in statistical physics, of course. This is here New York census in 2010, and different colors indicate different ethnicities. And you, of course, when you see a map like that, you wonder, is it the result of public policies or a natural way the system flows, self-organization? And this heterogeneity has been underlined in the book of Thomas Schelling, Micromotives and Microbehaviors. Okay, so this was just to introduce this broad question. And I'm going to introduce now the model. What is the Schelling-inspired model we have? So we have here only one type of agent, okay? So you forget now the tuple population model that you may have in mind in the Schelling papers, that they occupy a city, a discrete city, and the satisfaction of every agent, so in black here, depends on the neighborhood density. And this neighborhood density should be neither too high nor too low, because people don't want to live in overcrowded neighborhoods and they still want to have a nice city life. And they want to maximize their utility, which is the function of the density. This utility is, let's say, peaked at some target density, local density, and agents will average around them, and we look around them at some distance sigma. Okay, so you can take any kernel you want with a finite variance. And if you do that, you have this utility that depends on the local density, the local average density that agents see around them. Okay, so this is the basis of the model. And now the dynamics. The dynamics that we put is that you, at each time step, you select an empty site I. You select an occupied site I. You select an empty site J, and you ask the question: okay, will I jump from I to J? Okay, because the people in the city are allowed to move, and they're allowed to move actually anywhere in the city. Okay, not necessarily in their close neighborhood. So you have to compute the utility where you are, the utility where you want to go, and you jump with some probability. And that was a big question in the literature. Okay, what is the probability of jumping? Actually, this function here, we can leave it free. Okay, for the simulation, for the sake of the simulation, we chose the logit rule, but there is no reason to take this rule a priori. Okay, because actually the system is out of equilibrium, and even if you take a rule like that, you won't go back into an equilibrium dynamic system. And I will show you rapidly. So the type of function that you want resembles more or less something like this. So beta is basically the inverse of the temperature. So it encodes the fluctuation or the decision-making process. If beta is infinite, it means that agents are purely rational. If beta is equal to 0, it means that you have a flat probability, which is equal to 1/2 to jump. So every time you take an agent, an empty site, you have a probability 1/2 to jump whatever the utility where you are and the utility where you want to go. And with the increasing beta, you can interpolate between purely irrational agent and purely rational agents. This is the main ingredient, but the specific shape of this function is not important. Okay, so why is the system genuinely out of equilibrium? Well, you can take an example here of a very simplistic map, like even in 1D, where you have 3 agents in gray on 5 sides, and you find a cycle between these 4 states. Okay, you find a cycle that doesn't have the same probability to be seen in the forward way and in the backward way. And this is the so-called Kolmogorov criterion, but it's intrinsically related to the fact that when you have this discrepancy here, you have entropy creation in the system. Okay, so your system is genuinely microscopically out of equilibrium. And it turns out that if suddenly you reinstall locality in the system and you divide the city in fixed neighborhoods, as it was performed by Grovin in 2009, then you are in a kind of mean field dynamics that restores detail balance and equilibrium dynamics. And in that case, you have a miracle that happens, that occurs, and that you can describe the system in terms of a free energy. Okay? And so in our case, we remove these boundaries. We have a city where you look at any place you want to go. You don't have these neighborhoods, and you have a genuinely non-equilibrium system. Okay, so no questions so far? Okay. Okay, so what is the phenomenology of the system? You start from a homogeneous phase at exactly this target density. So you say, okay, everyone is very happy. And you run the dynamics. The utility of everyone is maximized. And it turns out that you fall into a suboptimal configuration. Okay. This is very annoying, and you would like to understand what's causing this. And one of the genuine reason is that once you start emptying a region, there is no way to repopulate this region. There is a statistical effect that once you flow out of this region, there are many other people that want to flow this region where the utility is not the best. And there are many other places where the utility is slightly better than the one they are actually. And so you create like that an empty neighborhood. Yes?
How do you define suboptimal?
Suboptimal with respect to the utility. Here in red, you condensate in this phase here, where the density, the average local density, is higher than the target density. And in that sense, when you compute the utility of each agent, it's lower than the density they had initially.
Yeah, but for each individual agent in that state,
yeah,
that agent is probably happy, because otherwise
it's not the best. It's not the happiest on earth, let's say.
No, I mean, if you were really unhappy, then you would start moving again, and you would move away from.
So they are actually, so they still might have like fluxes that you don't see here by the eye, because remember that it's a non-equilibrium system, so you might have microscopic or macroscopic fluxes that exist in the stationary state. Okay, I don't show them, but I don't know exactly what they are. It's not that important for now, but indeed. Yes?
And the size of this depends on the target density, I guess, or can you have multiple holes?
So actually, no, you cannot have multiple holes. This is a genuine phase separation, like a liquid gas, with a full phase separation without, like, there is no length, there's no typical length scale here. So you have a full phase separation in the end with a gas on the side, on one side, and a liquid on the other side. And here, just for the sake of the simulation, I took periodic boundary conditions, okay, for my two-dimensional city.
And can you control the size of this hole by increasing the target density? Or...
Yes,
So if you...
Yes, you can, because it will completely determine the phase diagram and the densities of the binodals. And from here, you have the double tangent construction, and you can know the size of where you have the gas. Yes?
One question about the domain size. So I guess at some point the density becomes bigger on the outside.
relations between the whole ring. Because they're unhappy because it's empty, and it gets too dense on the outside. So is this a function of domain size also beta? Is it a function of beta? Yeah. Yes, yes. If agents are purely irrational, you expect that it's as if they don't interact, so you expect a gas. So at high temperature, which is a low rationality, you expect that the system falls into a gas. At some point, yeah. But what happens when you vary beta? This just disappears at some point. So I'll show you. Okay. I'll show you. Yeah. And the domain size question. So because they're just here they want an optimal half, and they're equally unhappy if it's empty or if it's full. But if there's not enough capacity in the rest of the system, they will also be unhappy. So you're talking about finite size effect here? Yes. Here the system is large enough so that you can nucleate the empty region, if that's the question. Yes. If the system is small, then there is no room to nucleate this phase separation. Yes?
Actually, what would happen if you would have confinement, like instead of putting very wonder in this? Like that is it, you cannot.
Yeah, you would have the same phenomenology, exactly the same. It's not the boundaries are supposed to be like order 1 over L effect. I mean, it's a second order effect, the boundaries. So if the system is large enough, you don't care about the boundaries. Yeah.
You said there's no intrinsic length scale to the system. So I was wondering, so how many each agent and how many neighbors does each agent look to determine if it's happy or not at that place? So here, it's something that you choose. The sigma, the typical length scale of your interaction is something that you choose. It's not that important in the sense that it's always the same universality class. It's a finite range interaction. Okay, so just to be clear, the interaction range is finite. The jump rate, the jump distance can be infinite, but it's not a big deal. And I'll show you that you anyway fall down into the Ising 2D universality class because you have an isotropic system, homogeneous system, speed 1 or 0, okay, so a 2-state system, and so naturally you will fall down into the Ising 2D universality class, even if the system is out of equilibrium. The fact that it's non-equilibrium, it's not important to be in the Ising 2D universality class. Okay. And just to show you that you have a similar phenomenology with different utility functions. Okay, so here different colors for different utility functions. The same hole that appears. The funny stuff is that you have condensation at the edge of the dense phase, and you can understand that. It's because here you have a higher density, here you have an empty density, so people at the edge are happier than people in the bulk somehow. But yet, even though they are happier, you don't nucleate microphase separation. So that was the puzzling physical effect, the puzzling phenomenology, that people want to condense at the edge, but still you have only one boundary and not multiple boundaries. Okay? And I will try to explain this phenomenology. This is what I call density overshoots at the edge.
Does it make any difference if it's not symmetric?
Yeah. The utility function?
Yeah. I mean, will it then? Yeah. I mean, because they're all symmetric, right?
Yeah, they're symmetric, but
it doesn't matter. But
no, it doesn't matter. You will get the same. Yeah, the same phenomenology. Yeah, it's not that important. Okay, so this is the phase diagram with extensive numerical simulations. So it's really, as you can imagine, a liquid gas phase separation. Okay, where you have your critical point, you increase the temperature, you reach the critical point. You can measure in your simulation the other parameter, the susceptibility, and it turns out that you fall down into the Ising 2D universality. Okay. You have a strong finite size effect, so you have to be careful with the simulation. But anyway, you fall down in the Ising 2D universality class.
And so we would like to get analytical insights on, for instance, the dense phase that you reach here. Can you predict the density, the suboptimal density that you will reach? Okay. And for that, we were wondering, okay, it's a system where particles can jump anywhere. So we don't have tools. We don't have hydrodynamic equations, or it's difficult to analyze these hydrodynamic equations where you have a motion of infinite range. Okay, so maybe that the fact that jump range is infinite is not that important. And also the fact that there is no macroscopic fluxes in the stationary state shows that the dynamics in the stationary state might not be that important. So we looked at the coarsening dynamics, okay? And here, if you start from a homogeneous phase and you let the system coarsen, you find that the domain size grows at T⁻⁻. This is a finite size effect, but it's not a big deal. It's just to say that, okay, within the experiment, indeed, our system behaves as if the jumps were local, actually. And so this is why in the following, we are going to do a local move approximation. So basically, you have many ways to do that, but basically doing a Taylor expansion on the jumps. And this is what I'm going to show now. Yes?
When you say infinite range, I mean, do you then have a distribution for the jump size?
No, you can jump anywhere in the system.
Just uniformly everywhere
in
the system.
And do you have a plot showing how the domain size depends on the system size?
I don't have the plot.
Because you only check the dynamical scaling.
Yes, so okay, so rigorously, if the system is very, very large, this should be a T⁻⁴ behavior.
Okay. But this is the time dependent, the dynamical scaling.
Yes.
What I mean is the system size, like and the domain size, how the domain size depend on the system size.
But what do you mean the domain size?
Yeah, the cluster.
The cluster, but the cluster in the end, you know that it's a given fraction. Yeah, it's only one cluster, so it's always the same fraction of the total system size.
I see.
In principle, 1/3 scaling is very classic.
It's classic when the moves are local. Yes, it's in the Canillard dynamics or Kawasaki dynamics of Ising spins. Yes. And so what I suggest is that we do a Taylor expansion to have something more familiar. And of course, okay, the total number of particles is conserved. So you know that you have to fall down into this conserved equation. Okay, the total density rho is conserved. And what is now the current? The current is a sum of a deterministic part and a fluctuating part, okay, with the mobility. So if you don't allow the people to overlap, the natural mobility that comes in is this one, rho times 1 minus rho, and mu, the chemical potential. So here is the flux, the total flux, or the deterministic flux of your equation. This is the mobility times the gradient of the chemical potential. And the chemical potential is a sum of two terms, an entropic terms, and a utility term that is related to the interactions between your socioeconomic agents. Okay. What is interesting is that this chemical potential is not the derivative of a free energy. And because of that, this is not we said that the system is not gradient, and you can show that at the level of the macroscopic hydrodynamic equation, you create entropy because of that. Okay, because you cannot. There's no way to write the chemical potential as the functional derivative of a free energy. And the deep reason is because the utility of phi, of your perceived field, is a function that is non-local in the field and non-linear. If you were to have a linear interaction, you would recover somehow a pairwise interaction between your agents, and that you can map onto an equilibrium system. And if the system, or if the density was computed in a purely local manner, you would recover an equilibrium system. Okay. And so here is where we are going to leverage the recent technology of active matter systems, where we understood that in this kind of active scalar field theory, you could perform a change of variable on your density, okay, a local change of variable, from which you can assess the local properties of each phase and perform a double tangent construction, just like you would do for an equilibrium system. Okay? But this object here, this functional G, is not free energy. It's not by minimizing this object that you would get the answer. It's not a Lyapunov function of the system. It's an object that we still don't know the status, actually. But it turns out that if you do the double tangent construction of this object, you can predict the phase diagram and the binodal densities. So this is why this is what I mentioned here. You want to find the change variable so that you restore the Schwarz condition. The Schwarz condition is just a way to say, okay, there is a potential function from which we can derive from which you can find the chemical potential. And so to do so, you perform a gradient expansion of your chemical potential. You identify the lowest order terms in terms of the gradient expansion. And this change of variable must solve this equation for profound reasons of a change of phase. When you go across a phase, you have to cancel some terms. This enforces this change of variable, and with that, you're able to identify your big functional that will be useful. Okay, so what we do is that we do this expansion. You have this utility, and so since you have the utility, you have the chemical potential. You expand in terms of sigma and the different derivatives of the utility. You identify your different coefficients, and you end up with your change of variable that is of interest. And here comes, okay, this is a very niche comment, but it's interesting still. Here comes the understanding of why you have density overshoots. It's because here in the field theory associated to the expansion, the term that would be classified as the tension, at the surface tension, like you would have in equilibrium, becomes zero and even negative. And since it's become negative, it's the next order term that appears and that becomes relevant. And this is typically what you have in Helfrich Hamiltonian of membranes, okay, where you have the tension that is zero, but because of the bending stiffness, you might have overshoot of the height of your membrane. And this explains actually the overshoot of the density. It's because in your expansion, you have the fourth order term that becomes relevant and replaces the tension, the classical equilibrium tension that you would have. Okay, this was the reason. Okay, so you do your double tangent construction, and you can predict like that the binodal. You reconstruct the phase diagram, and you get the line on which you're going to fall when the system phase separates. Okay. So this is a summary of what we have so far. We have the spinodal decomposition here in this region that you can predict by simply linear stability analysis of your dynamics equation. And you have this region in blue where you have metastability, and you need a nucleation scenario to leave the homogeneous state and reach the phase separated state. Okay, and before going to the next step, okay, what are the natural extensions of this system? So no questions so far? Okay, the natural extension. So as Schelling, we would like to restore some diversity among the agents. So for instance, if you have two types of interacting agents, what are the possible interactions between them? So you might have a cooperative interaction. So it all depends on the utility of each agent and the utility with respect to one another and the local perceived density of others. If you have cooperative interactions, here you expect well-mixed system. So here they basically overlap, or they basically co-locate. Every time there is a pink agent, there is a green agent. If you put repulsive interactions, you expect a full phase separation, okay, naturally. But you can also put frustrated interactions, as depicted by this small schematic here. So green loves green, green doesn't like pink, but pink loves green and pink. So you would have a condensation of pink that is triggered by this interaction, a condensation of pink to green, but green that wants to flow far from green, okay? And if you do so, and I can show you the movie. Yes, basically, so it becomes a non-reciprocal interaction. And this is a typical simulation that you would get. What is funny here in the system is that the moves are still non-local. So I simulated the full system with non-local jumps. Okay, so you have blobs that flow, but at some point, a blob, when the frustration is too large, can just vanish because it can jump anywhere else in the system. Okay, there is no continuous flow of the blob because the particles can jump at some point. So this is where you see the chasing instability. Okay, so that was a funny movie. And another natural extension would be to introduce another field in which you can couple your density. A natural field would be the price field, of course. On the data, I didn't show the data here, but in France at least, there's a strong correlation between the price and the density, as more or less the price is high when the density is high. So you could imagine that you have a penalty when the price is high, and you adjust the utility as a function of this penalty. So psi is the price field. And as I said, you assume that the price, so the penalty is proportional to the price, that is proportional himself to the density. And in the end, you have let's say a simple with a simple linear dependence between the price field and the density field itself. You put it in the utility function, and like that, this effect of the price just appears as a pairwise repulsive interaction between agents. So the price can partially destroy condensation. The physical effect of the price. And a colleague of mine, Antoine Sirus-Bechara, along with Michael Benzenken and Jean-Philippe Bouchot, have studied more deeply the correlation and response functions of the price, of the housing price in France in the last 25 years, I think, where they have measured the correlation and response function, and they could understand that the price of the housing behaves as a stochastic field, diffusive stochastic field in 2 dimensions. And so what is interesting in this kind of study is that you know the response function, so you know how the price will react when you open, for instance, a train station at this place, a metro station at that place, a museum at that place. So this will help public policies, okay? This is the hope, at least. Okay. Yes.
Did they find similar behavior, as you said, about the housing prices that is proportional to the density, or did they find some other function?
No, they do find that. I mean, it's from the data that I found that the price is more or less proportional to the density. Yeah. Okay. And so this is where we go to the last part of the talk, which is try to have a deeper understanding of this 2 population model. So what are the 2 populations that we're going to consider? the problem in the previous model, it's not a problem, but it was a choice, that agents were seen as purely selfish. Okay, so it might be too strong, and you might also prevent the vision of a public policymaker, okay, the state, central planning, okay, and you miss somehow some complex interactions. So we decided to introduce another type of agents that are said to be altruistic. And these agents will move according to a utility, which is the global aggregate utility. So as if a state was telling people to move from one place to the other because it's better for the city or for the society. So this utility is just the integral, just the sum of the total utilities weighted by the density. So this is a definition in if you have a continuous system, but of course the definition would be exactly the same for the grid. Okay, and if you do so, you can rederive your hydrodynamics equations. The total number of agents is conserved, so you now split between a fraction alpha of and I didn't say it. Okay, between alpha of the altruistic agents. So you have 1 minus alpha of individualist and alpha of altruistic agents. So the equation for individualist equation will be, of course, similar to the previous one, where you have the mobility that is now proportional to the density of individualist times the 1 minus the total density. Still, you have the gradient of a chemical potential, and this chemical potential, just like before, has no reason to be the derivative of a free energy. And you still have the noise. And for the altruist, now you have, I mean, still this mobility, but you have a system-wide objective function, which is the macroscopic utility. And here the free energy is, as expected, the sum of your system-wide utility and the entropy, the mixing entropy. I missed a plus somewhere. Yes, okay. That would naturally occur in your equilibrium systems. But nonetheless, because here it's not the same function here and here, the system is out of equilibrium, and this is what we can call a non-reciprocal coupled hydrodynamic model. Okay? Okay, what are the limit cases? So it turns out that alpha is equal to 0. We just have seen it. We have understood the behavior of the system. We can predict the spinodal, which is here in dark blue, given by the linear stability analysis. We can compute the binodal by the generalized thermodynamic construction. When you have altruist only, the system is a pure equilibrium system. And so you can actually compute everything semi-analytically. So you have, again, the spinodal, the binodal by construction, because you have the free energy. You have constructed the free energy like that. And a funny story, I mean, funny phenomenology is that the binodal never goes beyond this objective density or star. Okay, so the altruist at most will converge when the rationality is the best, let's say, they will converge to the best possible outcome for the system. So there is never suboptimal aggregation when people are really trying to maximize the state utility. And the question is what happens for intermediate values of alpha, okay, when you have a mixing between altruist and individualist. Okay, so this is the behavior of the spinodals. What do you see? You see that when alpha is increasing, so when you have these people that care about the general welfare, you increase the critical temperature in the sense that you're more robust to fluctuations. Okay, your phase separation is more robust to fluctuations. It's not weird. I mean, something that we could have expected. Okay, because it's beneficial for the system to have a phase separation when you have more. I mean, no, it's not trivial actually, but okay, it is what it is. And for the binodals, what is interesting is that as soon as you put a small fraction of altruist in the system, the binodal here directly jumps at the optimal density, in the sense that you have what resembles a catalytic effect of altruism. And this increase of alpha just kills the suboptimal aggregation. Okay, and this is what we want to understand in the following. Okay, and here I just illustrate the phenomenology of the system. We start from a purely individualistic system, okay? So we are on that homogeneous phase that is supposed to be the optimal one. It turns out that they fall into the suboptimal cluster. And now at time t is equal to 0, you just you put in orange, I don't know if you see that, but there is a given fraction that becomes altruistic. Okay, and you let the system evolve. And what's happening is that these altruistic agents are going to be settled at the edge of the system. And by doing so, they're going to close the gap and they're going to restore the homogeneous optimal or optimal utility function for the system. Yeah.
Are these agent-based simulations or simulated the SPDE?
This is the agent-based simulation. This way. Yeah. And what we say that it has a flavor of surfactants, just like we have in soft matter. Okay, when you put soap at some interfaces. So this was reminiscent of that, and we will try to leverage this vision. Okay, and at higher temperatures, here the system is supposed to be stable in that state. And if when you add these altruistic agents, you do observe the phase separation. Okay, here I didn't see the fact that you phase separate, but you trigger phase separation when it's beneficial. Okay, so how can we understand this behavior? And first, the naive approximation would be to consider a well-mixed system. And actually, this is very efficient. We didn't expect that to be that much efficient. The idea is just to say, okay, it's a mean field, well-mixed system where agents can now be altruistic at times with a probability alpha. And so your chemical potential is just the weighted average of the individualistic chemical potential and the chemical potential for the altruist. And if you do so, you just have one equation, one hydrodynamic equation, and you can play again of the binodal construction with this one single hydrodynamic equation and build your generalized thermodynamic framework with this equation. Okay, and this works tremendously well where, of course, at 0 and 1 by construction, and where the system is well mixed, meaning that at the edge of the binodal, when you know that if you go above the binodal, the system is anyway in a one phase, and so it's well mixed by construction. So it should give the correct binodal at high temperature, and this is the case here. Here I compare here on the left is the true original system, on the right is the approximation, and you see that you have a perfect overlap close to the critical point of the binodals. Okay. Yes.
Get more information about this chemical potential flow. So what is new are the individual one is the constant, and the other thing now we put the second one as a form of a derivative or a sort of free energy. The very mixed chemical potential. Can you explain how did you deduce this form?
How did I deduce this form?
Yeah. One part is
Yeah. So there is no, I mean, it's just a brute writing of the well-mixed system. There's no, I guess you can derive it, but it just that you just mix your two populations, and so the chemical potential has to be a mix of these two chemical potential. I don't have any other better explanations than that.
the second, the one individual. Can you explain again the second one for
This one?
not the second? Yeah,
This
maybe both actually. Yeah.
both? Okay, so mu I was that. Mu I was the sum of the entropy term and the utility term. Okay,
Does that include your part?
it's a non-equilibrium contribution. It turns out that this one, there is no way you can play with it. There is no way that you can write it as the derivative of a free energy. Okay, this one here, F, is the sum of the global utility function and the entropy. And it turns out that when you compute the derivative of it, you get the natural chemical potential, and exactly the chemical potential that you have for this population, for the altruist. Okay, and then I just say, okay, I'm just going to mix these two chemical potentials. Okay. Okay, and so we're getting to the end, and just before finishing, we wanted to understand more quantitatively the role of these surfactants, or these altruistic people being surfactants, and a way to quantify it would be to look at the nucleation rate in the binodal. Okay, can you trigger the phase separation, or can you inhibit the phase separation when you have these surfactants? And it turns out that because of this formulation in terms of scalar field theory, you can use recent results for nucleation theory in active systems. And you know that the nucleation rate actually depends, just like in equilibrium, depends on the quasi-potential over the typical amplitude of the fluctuations. This is basically a change Arrhenius law. Okay, you have you're in a metastable state. You have a rate to escape it, and this rate is given by the cost, the total cost to escape the homogeneous state divided by T, the typical amplitudes of the fluctuations. So this is what we were trying to measure first in the, I mean, not in the simulation. Here it's more analytical approach. So we define this pseudo surface tension that is relevant to catch the total cost to escape the homogeneous state. Okay, this pseudo surface tension comes from the expansion that you do, the second order expansion that you do on your field theory. And you measure this pseudo surface tension with respect to the distance to the critical point, and you look at the evolution of this quantity, which is the surface tension, and you assess the quasi-potential as a function of the fraction of altruists in the system. Okay, and what we observe is that close to the critical point at high temperature, you have a drastic decrease of the chemical potential when the fraction of altruists increases, which means that you have a huge facilitation of the phase separation when you increase the fraction of altruists. And this was illustrated by this plot here. This is what we expected, but here we can quantify it from this recent progress in
active matter theory. And this is just for illustration of surface tension, okay, in the realm of soft matter, okay. But there is a link between this surface tension and this surface tension, but keep in mind that this surface tension from the gradient expansion in non-equilibrium systems is still a matter of debate. It's not obvious, okay. It has many meanings. The mechanical meaning is not clear, so I leave it for a future presentation. And for that, I will leave you with the take-home message. So what do we have? I have presented the Sakoda-Schelling model out of equilibrium, and we saw that the results were absolutely were quite robust to the utility function that we chose. That was one of the first objectives, and to the decision-making process that we have. In the theory, nowhere I have to use the fact that I use the logit rule, okay, the jump probability as exponential of, I just need to do a Taylor expansion at some point, but the exact shape of the function is not important. And then we suggest two different models for individualist versus altruism. They are nearly identical close to the critical point with the well-mixed approximation. They have striking differences when the rationality is low. And what it tells us is that it seems that the action of a central planner is very important, okay? You cannot have well-mixed system every time. You need at some point to have someone that tell people to move because otherwise the system is suboptimally organizing. So that was, I would say, the main message of this work. And with that, I thank you very much all for your attention.
For this very interesting talk. Are there any questions? You already have a bunch of them.
Yeah, I mean, it's maybe a silly question, but this moving, being smooth over the utility, I imagine equilibrium is easily attained if there's some threshold that needs to be passed. So you've got this probability of moving, which is positive quite often, I guess, depending on the temperature. But if you have, say, you need a big enough utility increase in order to move, so you've got some, you know, like you would have in the real world, that I mean, I'm not moving into every house that is a little bit better for me.
Okay.
Yeah, if you have this barrier to moving, then I guess there would be lots of equilibrium states. I don't know if they're reachable.
So you mean stationary states?
Yeah, sorry, stationary states.
Okay.
I mean, does that matter very much for the story at all? Would you see some way to think about your results in light of that kind of
okay, I don't know. We haven't explored the fact that maybe there are multiple metastable states accessible to the dynamics, if that's the question.
I mean, in my mind, if there's some threshold for how big this utility increase needs to be before I move, then I get actual stationary states, like.
But so you could have you could be locked somehow into the. Maybe I'm wrong, but you could be locked because of the microscopic dynamics, because of this threshold. But at the hydrodynamic level, this would vanish maybe. Okay. I'm not sure, but it might depend then on this very specific of the utility function that you define, and I don't know.
Maybe slightly related because the original Schelling formulation was also formulated in a kind of threshold model, right? You have critical, you have a fraction. If your local density falls below that fraction, you move, otherwise you don't move, which you can probably also formulate in terms of this sort of smooth element function, like not a step function, but make it like a logic function. But that's different than a logic function of a utility gradient. Sure. Because if you have a threshold model, you can get frustrated, like you can get trapped. You see simulations of Schelling model, you see there's also a phase where you get stuck in suboptimal because there are no locations available for improvement or increasing your utility.
Okay,
Is that something you see in the hydro limit?
But when you say stuck, so where I'm not sure of is that is it related to the discrete nature of the agents themselves? Because sometimes I think you have the feeling that it's stuck, but if you really go into the hydrodynamic scale, the system is still flowing and you still have coarsening and you still when you look at the microscopic system, you have the feeling, oh wow, stuck, and the boundaries are not moving.
I can imagine the microsystem being stuck in a frustrated state, but imagining the hydro limit to be stuck is very more difficult because everything is smooth, continuous, and flowing. I guess the question is that something you can see back in your hydro? I know there are some Schelling papers, you know, that where they actually say that in this they call it a phase of the Schelling model where you are in the frustrated, and then frustration means something different than you said, like not the reciprocal, non-reciprocal, but it means that you know the agents cannot find locations where their utility becomes positive, so they are stuck in a suboptimal situation. Is that something you can see in the hydro as well? It's
not in my model, at least.
Because maybe he considers Newton field with the sigma, and in the drawing paper they consider discrete field like either 0 or 1 on.
In their paper,
they have this frozen phase, the phase at the boundary.
Yeah, they have frozen boundaries, and it's a fake 2D system, you see, because there is no on the eye it looks like 2D, but you interact the same way with a close neighborhood and a very distant neighborhood. You see, you interact in the same way. Not only like I mean, there's no interactions actually. The only interactions that you have are the one in your neighborhood, and so any other neighborhood, it's not interacting. Then it's a matter of jumps. But you could organize the city in a line, you would obtain exactly the same phenomenology. You see?
Because interaction outflow.
Yes, because it's a fully connected system.
Also, Mike first, and
Thank you. I was thinking that in this PD for a row that you wrote, when you had only one agent, 0 and 1 were also fixed points of this PD, like rho equals 0, rho equals
yes, exactly.
1. And if you simulate just the deterministic model, like you remove Gaussian noise, would you still find these bubbles? Like purely deterministic simulation of the PD. Okay. And do they behave differently once you have noise, or
no? The noise is just going to put fluctuations on the boundaries, and the noise is just here because I mean by construction you have the noise, you have this hydrodynamic noise, and the fact that in the end it allows you to assess the escape rate. If you keep track of the noise, you can assess the escape rate, for instance, when you're in the metastable phase. If you remove the noise in the metastable phase, you get stuck in your fixed point indefinitely. If that's your question.
But are they both stable, like 0 and 1, or you get stuck only in 1?
So 0 and 1, it just okay. The 0 and 1 is just that it's a local property, right? The density field can be 0 at some point, but it cannot be 0 everywhere because the total density is conserved.
Okay.
You see?
Okay.
So the total density sums to rho naught, and so rho is equal to 0 or 1. It's just a local property that you cannot go below 0 and not above 1. Just telling you that.
And another request. So you said that there is no detailed balance.
Yes.
But I was wondering if effectively there is no detailed balance, but once you have these bubbles forming, the entropy production is essentially only localized at interface, and far from interface is very little because it's
yes.
Okay,
It's what's happening, just
okay.
like they
So it is effectively there are two regions that are approximately detailed balance and one region which is very non-detailed.
You could say that.
Okay.
Yeah.
Yeah, so I had a question about the pricing and the question of policy. So one of the things that's known in the real world is that segregation effects are very long lasting. So if you look at the house prices of different regions of the city, they're pretty stable over 400 years. The rich neighborhoods stay the rich neighborhoods. And this is basically urban planning over centuries that has an effect on this city scale. So in the Netherlands, it's actually quite small. These blocks are kind of relatively small. So I was wondering, with your density kind of price model, you could make this differential between the two groups. So one poor, one rich, right? So the impact of density is less felt. Is there a way for you to put in these constraints on availability and pricing of the actual units and see how that affects your creation?
So your question is, can we map that in the data?
Yes.
And look at what's
maybe out. You get some kind of sense of a frustration in the city, right?
Yeah.
Given its urban history of urban planning, there'll be a natural tendency towards the system, and then that's a long-term policy, and then the kind of energy that you have to put in as a policymaker to overcome that your history.
So, I mean, short answer is I don't know. It should be done, okay, but it takes so much time to really dive into the data and have a proper cleaning, filtering of the data.
The good thing is most countries, the house prices kind of are public.
Yeah.
So you'll get some kind of characteristic of these cluster sizes.
In France, we couldn't, from the database I know of, we couldn't get before the 60s, but I mean, if you dig, probably you can.
There's a organization in the Netherlands called the Time Machine. You can actually see the historical urban planning 2 or 3 centuries.
Okay.
I don't know how much is house prices, but you get indications of when the buildings were made and
okay.
Smaller country.
Because the other thing is, certain cities also you have this gentrification effect, and that's kind of interesting for.
Of course.
Also, in the practical sense, measuring segregation, you have this problem of what area do you actually measure with and against. But this might be a way to kind of give some indication.
So I have to mention also that there's a very good paper by our colleagues, Denis Sierra, Martin, and the group of Vitelli, where they have used a similar approach of a hydrodynamics approach, trying to infer the different parameters from the data, the different coefficients of the field theory from the data. So sometimes it works, sometimes it doesn't work at all, but it's not a big deal. The ideas are very nice. So I encourage you to read this paper.
Okay, I myself have many more technical questions, but maybe we talk later. But I can ask one now. You mentioned in the beginning somewhere that when you take the agent-based model, you have this loss of the the forward rates and the backward rates are not equal, so you have to sort of out of the equilibrium thing. But you mentioned that if you start coarsening into neighborhoods, then you restore the equilibrium. I find it a bit. I have to see how that
I'll show you on the board.
I can imagine, I can make my neighborhoods as small as a single agent.
Exactly.
And then
this is what's happening somehow.
Why don't I have equilibrium in the single agents model? If I say my neighborhoods
you will have. No, you will have. If suddenly your utility, so because if you now put neighborhoods, your utility is not a function of a phi, it becomes a utility of the local density. It's very, very local.
Okay.
And because of that, you don't need anymore the gradient expansion.
Yeah.
And since you don't need the gradient expansion when you look at the chemical potential, you can directly write this as a derivative of a functional energy. So it's really the fact that you, as soon as you have locality in the utility, you don't need the gradient expansion, and thus you recover a free energy, a macroscopic free energy.
That was then probably also the answer to another question I have. Like, can you choose in the individualistic model? Can you choose your utility in such a way that you do have this gradient expression? And
So this is a way.
Make a local.
Yeah.
Make it local.
Even if this is nonlinear, if this is local, you will have free energy density.
And that's what your colleagues in Italy did. Italy group did, right? They have a utility that's just local function. I remember
they did something. So to be honest, they did something a bit more fishy, but it's okay. Since I said something nice about the paper, I can. They add
the gamma
at the level of the microscopic itself. They add gradients stuff, which doesn't make any sense to me when you look at the rules. Okay? A person is not looking at the gradient, at the second order gradient, when moving elsewhere.
You have to do it, otherwise you're numeric.
And they had to do it because they had to recover the stabilizing terms in their gradient expansion.
Apart from the reason for stabilization, they also interpreted that term as a surface tension. They explicitly mentioned that. So you want to incorporate the surface tension effect by hand, and then they plug it.
Okay.
By the way, I have one question regarding the first part. Maybe you go a bit quick and I forget it. So you mentioned about the macroscopic flux vanishes at the steady state rate, if I remember correctly.
When you look at something like this?
Yeah, you say something macro. Yeah. How can you check it? Because it's required to know the full distribution. Otherwise,
no, you're right. It's okay. I was very blunt. It's just looking at the movie of the simulation, you don't see any macroscopic fluxes.
Because otherwise, you can follow this recipe by Gene Wang. You can decompose.
No, but I agree. If you really look at the probability flux, at the probability fluxes, they are some.
Okay.
Because the system is non-equilibrium one. But if you do this screwed up, imagine that you take this to 0, you solve your system, so divergence of the current is equal to 0. I mean, you just solve your hydrodynamic equation. In the end, when you look at J, the current is 0. When you look at the deterministic system, the deterministic macroscopic hydrodynamic system, J in the stationary set is 0. So it's not the probability current, it's the macroscopic hydrodynamic current.
Actually, J is 0, not the gradient J is 0.
J is 0. Okay. Yes?
Is it possible that these fluxes are like, so I imagine that if you only put the deterministic model, you could sometimes see that these bubbles are stationary, sometimes maybe shrink and sometimes maybe grow. Is it, or you only see one of them?
You always fall down into the big phase separation. So
because of the conservation.
Yeah, you have coarsening, and so in the end, you know that you have all the liquid on one side, all the gas on the other side.
Because I would expect that, like, if the deterministic limit has a stationary bubble, then I would also have no fluxes in the stochastic correction, like in even on the interface.
As soon as you put the stochastic term, you will have probability currents, and
in both ways.
In both ways, yeah.
Okay. And would they balance
necessarily if you have reached a stationary state, I guess.
Okay, we can keep discussing over lunch as usual, which is served downstairs. I do have to note, by the way, that we were notified by the secretaries that they need the room starting at 1:30.